So one of the most useful aspects of magnetism is the concept of induced EMF and something called magnetic flux. So to understand this, first we need to know basically what is induction. Okay, so an induction is basically just to cause a change. You induce something to happen. So in physics, induction is causing some kind of change to occur. Okay, and change in physics is also called a flux. Okay, so what is flux? What is, in particular, magnetic flux? And since physicists love to use equations, we have an equation that describes magnetic flux. Magnetic flux is equal to the capital Greek letter phi. So that's kind of a circle with a line through it and two lines up, top, and below, is equal to B times A times cosine of theta. Or again, this weird looking symbol, that's called the Greek letter phi. That is the magnetic flux passing through an area. A is the area that you're going through. And we'll draw a picture so we can see what that looks like. B is the magnetic field. And theta is the angle between the area, which we should know how to figure out the direction of area from previous lectures, and the direction of the magnetic field. So if I have, let's say, a square, a flat sheet, and I have some magnetic fields that are going through this sheet. So it goes in, comes out the other side. The line that comes in and it comes out of the other side. So that's a magnetic field, and it's passing through this area. So if I combine the size of this magnetic field with the size of this area, I get a magnetic flux. Okay, that's a change in magnetic field passing through this area. And the angle theta is the angle between the area, which again, the direction of the area is perpendicular to your surface, and your magnetic field. So in this case, my theta, since my area and magnetic field are the same direction, is going to be 0. It doesn't have to be. We could have a magnetic field acting in a different direction through an area, so we could draw, again, a little sheet. And I might have a magnetic field that now is going kind of in this direction. So my magnetic field comes in. The direction of my area is still perpendicular to my surface, so that's my area vector direction. And my magnetic field is kind of going off at this angle. So my angle in this case would be this theta, whatever that angle is. So it doesn't always have to be 0. It could be something from 0 to 90. Since we have an equation, we also want to know units of this equation. So the units of magnetic flux are going to be the units of B, which is Tesla, times the units of area, which are square meters, times the units of the cosine of the angle, which are unitless. So the units of flux are the Tesla times the square meter. So magnetic flux equation and magnetic flux units. Now I can use this magnetic flux to actually get to an EMF. Any time that I'm changing my flux, that creates or induces an EMF. It induces some voltage. Okay, and we've talked about this before. When you have changing currents, you create fields, you create magnetic fields. And there's a law that describes this called Faradays Law of Induction. So there's a few different laws for Faraday's law of induction. Induced EMF, first version of Faraday's law. EMF is equal to negative N times d phi dt. Now this is the calculus definition. This is the official definition, but since we're not in calculus, we can actually simplify this a little bit into negative N times delta phi, a change in phi, so that's a change in flux, divided by a change in time. And in fact, that's all the derivative is. The derivative is just a change in something. So that's calculus, and we can write it algebraically as a delta, as this little triangle. It's the change in flux divided by a change in time. And this is flux induced inside of a coil. So EMF 1 is for a coil of wire, something that looks like this coiled up loop. Okay? And if you're doing this induction inside of a coil, you have N is the number of turns in your coil. So according to this little loop that we have drawn over here, I have 1, 2, 3, 4, 5, 6. So for this particular loop, N would be equal to 6. And then my induced EMF would be equal to the change in the magnetic flux over the change in time. Change in flux divided by change in time. And that'll give me the induced EMF. Now the one thing that looks a little odd in this equation is this negative sign. And this comes from something called Lenz's law. And it means that that negative sign means that the EMF creates a current that resists any change. So the EMF creates some kind of current I that's going to resist a change. So what does this all mean? In particular, what does this negative sign mean? That I will induce an EMF that resists change. Okay, so it's not some kind of protest or anything. It just means that you'll create an EMF inside of a coil that tries to counteract anything that you do to change it. So let me draw a little loop of wire, and let's say there's really nothing going on in this loop. And initially, I have some magnetic fields going through this. 2 magnetic field lines going through this. Okay. So what I'm going to do is I'm going to send my magnetic fields through this, and then I'm going to induce a change. I'm going to increase the number of magnetic field lines that go through this. I'm going to put another line going through here. So this is my original magnetic field. I have 2. And then I add in another one. We'll call this B additional. So I've created an additional magnetic field going through this. I've increased the magnetic flux by increasing the B. Now, this coil, this little loop of wire, doesn't like that. This coil, this loop, doesn't like this additional magnetic field. So what this negative sign tells us is it's going to try to create some magnetic field. It's going to create some current that's going to create or induce a magnetic field that's going to go backwards. So be induced. And by doing that, I've created a magnetic field, B induced, that cancels out this B additional. So these two cancel each other out, and I'm back to just 2 magnetic field lines going through this. That's what this negative sign does. It tries to cancel out any kind of change that you have. It turns out to do this, I could create I could induce some current inside of my loop that would be going kind of this way. Kind of in this kind of direction around the loop. And we'll work on some problems and practice with that kind of concept. But conceptually, that's all this negative sign means. This negative sign means that I want to resist any increases, any changes that I have in my magnetic field. Correspondingly, the opposite could be true, right? So if I draw a loop and I have a magnetic field, I have two magnetic fields going through this. We'll call those the originals. This is where the state of the system wants to be. It wants to maintain this, two magnetic field lines going to the right. Now, if I create some flux and I create an additional magnetic field somehow by changing the flux, that's going the backwards direction. So this is my additional magnetic field. I change my flux. So I've gone from three magnetic field lines, or two magnetic field lines going to the right, and I've canceled one of these out so that now I only have just this one going through the loop. Now the loop's not happy about this. It wants to resist this change. It wants everything to go back to normal. So it's going to create a magnetic field that's going to go opposite. So this is going to be the induced magnetic field direction to resist the change, to resist the decreased magnetic field. So these two will cancel each other, and I'm back up to my original two magnetic field lines. That's what this negative sign says. I'm resisting any change in magnetic flux. That is what Lenz's law tells us. So anytime we're getting some kind of flux, we're going to induce some EMF. The first way we can do that is to change the magnetic field. Second way is we can actually just move an object inside of a magnetic field. If you move an object in a magnetic field, you are changing the magnetic field in it. You are changing the flux that goes through it. So you induce EMF. We call this motional EMF. Motional EMF is a result of movement of an object inside of a magnetic field. And your motional EMF, E, is equal to B, your magnetic field, times L, where L is the length of your object in the magnetic field, and V, which is going to be the velocity of the object moving through that field. This is going to be EMF from motion. Okay. And anytime you get this conductor moving in an EMF inside of a field, you're also going to induce some current. So induced current through motion actually has a specific name. So as a result of moving inside of a magnetic field, you induce some EMF and you induce some current, and that induced current has a name. It's called an eddy current. And this is what interferes with medical equipment and has to be taken into account when you're doing MRIs or CAT scans or anything that involves using magnets. So you have to worry about these eddy currents, which can kind of interrupt or interfere with what you're doing. The final way we want to talk about EMF and induction is with the concept of something called an electric motor. So electric motors are motors that are going to rotate due to electricity, and they're going to create some EMF too. So an EMF inside of an electric motor, the electric motive force of an electric motor is N times A times B times omega times sine of omega t. This takes us back to some physics 1, where N is the number of turns in a coil of wire. This is how you create an electric motor. You coil some wires. The number of turns in the coil is N. A is the cross section of the coil. So usually it's a loop of wire. So that would be the area of a circle in most situations, in many situations. B is how strong the magnetic field is that you're rotating this coil inside of. And omega is the rotational velocity, so how fast you're spinning this coil inside of this motor. So we have a coil of wire that's going to be spinning around. We're going to be rotating this. The speed of that rotation will determine what your EMF is, along with the number of turns, the area, and the magnetic field.